All right, lesson 5.1, Centroid. This is going to be a little bit different than the statics. We're taking a little bit of a break maybe from statics, at least from a force point of view. And we'll talk a little bit about geometry, and centroid is a geometric property that we're going to end up using a lot in statics. And if you go on beyond statics into strength of materials and other courses like that, fluid mechanics, you'll use centroid there. Our objectives are to be able to determine the location of the centroid for a body, and then also determine the location of the centroid using the method of composite bodies, and that's for shapes that are made up of multiple smaller shapes. All right, so what is the centroid? Well, the centroid, often denoted C, is the point defining the geometric center of an area. It is similar to the center of mass and center of gravity, but the centroid is dealing purely with area, not mass or weight. So if you have a constant thickness material that's all made of a homogeneous material, like constant density everywhere, then the center of mass and the center of gravity and the centroid all line up in the same spot. So it's good to think, or maybe it helps to think about the centroid from the perspective of center of gravity. If you think of your areas as flat plates of constant thickness and constant material, like a steel plate or a ceramic plate or plastic plate or something, and balance it on the tip of a cone or your finger, the centroid would be that balancing point. Now, that really is a center of gravity, a center of mass type of way to see it, visualize it. But again, if you think about it as a constant thickness, constant density, then it starts to make sense. A nice little tidbit: if an object has an axis of symmetry, then the centroid lies on that axis. So the centroid is usually a point, the point that you can put your fingertip and balance the shape. But if there is an axis of symmetry, or axes of symmetry, then the centroid must lie on those axes. So if you can find two different axes of symmetry, then you've actually found the centroid. If you have one axis of symmetry, then you know at least that the centroid lies on it. So for instance, for this quarter circle right here, there would be an axis of symmetry running right up through there, and you can see that the centroid lies on that. Here we have an axis of symmetry because the triangle can fold down upon itself. So you don't have to do any calculation whatsoever to find at least that line of symmetry and the line that at least the centroid lies upon. In some cases, the centroid may not be located on the object. So here we have like a washer or a ring. The centroid is actually in the middle. So yeah, I know I was saying put your finger underneath the centroid location, hold it up. Well, you're not going to be able to do a very good job with that one because it's not actually touching the material. Same with this angle here. That was just to kind of help you visualize it. And keep in mind that, it doesn't have to lie on it. If the area is made up of a common shape, this is one of the ways to determine the centroid of an area. Okay, we're going to learn several different ways. The first is if it's made up of a common shape, a quarter circle, a circle, a half circle, a triangle, a rectangle, you can find the centroid as they give you the formula. So here, 4r over 3 pi. That's straight at where r is the radius of the circle made by this quarter circle. And it's the same in the x and the y because it's a circle and it's not an ellipse. But anyway, the centroid is there. You can just pull that straight out of a table. There's a table in your textbook. The FE manual has tables for these. They're all over the place. The internet. This triangle here, this is a common one. We're going to use a lot. Triangles are extremely common, especially in statics. We are going to see that the centroid is at 1/3 the distance from the tall side of a right triangle, or 2/3 the distance from the pointy end of a right triangle. And it's the same in both directions. It's 1/3 away from the tall side of the right triangle, and 2/3 the distance from the pointy end of the right triangle. So if you do want to use one of those tables, just make sure you match the picture exactly, including where they're setting their origin at. And then you can locate the centroid from that. Another way to determine the centroid of an area is if the area is kind of defined as a function, like one side of it's a function. So like this is a shape that's the area under this curve of some function f of x. Then you can find it using calculus. And when I say under, it can also be kind of over, but bounded, because in this case over here we could actually make this x is equal to f of y, and then it is under the curve, at least from that regard. There's various ways you can do this calculus. In any of these ways, what you're going to end up doing is defining a differential area that has an area of dA. And that's either going to be from a vertical element or horizontal element. There's like polar coordinate elements, all of the different kinds of elements as well. But we're sticking purely with like x, y here. So you either have a vertically oriented element that's going to have a width of dx and a height equal to the function itself, so y. Okay, and then its centroid, the centroid of the differential area, is actually half that height. So y tilde, which is the centroid of the dA, is going to be equal to y over 2. Now, its x location of centroid is actually just equal to x for the function, because that centroid is right in line with this differential area. Keep in mind that differential area is a rectangle. The centroid of that is going to be right in the middle. So that dot is the centroid of it. All right. If we have a horizontal element, then we have an element that is dy tall, and then it is x wide, at least in this picture. And its area then is going to be equal to x dy. And its y location of centroid is going to be equal to the y of the function, and its x tilde is going to be at x over 2. Again, at least in the way that we drew this. For each one of these, you'll see that there's more complicated kind of shapes that you might have to subtract one function from another if you have multiple functions. Who knows? Or if you were doing a horizontal element of the one on the left here, your differential element would be over here, and then all of a sudden it's not actually x wide, it's actually your upper bound of integration minus x wide, and then it's dy tall. And where is its centroid? Well, it's not going to be at x anymore, or x over 2. It's actually going to be at your x value plus half the distance between here. So it would be like x plus the upper bound divided by 2. So it can get more complicated. You just need to be able to draw this differential area. There's usually a easier element, meaning vertical or horizontal, an easier element to use in one problem than another. That's what I'm saying. The choice can vary problem to problem. And even between finding your x bar for the problem and your y bar for the problem, you could even use a different element for the two different calculations, because you basically just run the same calculation again. You'll see it in a second. All right, you're going to need to just determine your coordinates of x tilde and y tilde, like, basically do what I did here. Draw this up. And then you're going to have dA, but you're going to want to turn dA into the width times the height. So in this case, over here on the left, it'd be dx times y, or y dx. And this one here would be x dy. So you're going to get dA in terms of one of the variables, y or x, whichever one that you are, that your function is written in terms of. So using calculus, this is how you find it. This is cool, right? You get to use calculus. Wow, that's pretty cool. You haven't done that yet in this class, and we're not going to use a whole lot of calculus in here, but in this particular part we are. X bar, the x location, the x dimension from the origin, from 0, 0 out to the centroid of this shaded area, is going to be equal to the definite integral from the lower bound to the upper bound. Sometimes that's from 0 to something. Sometimes it doesn't start at 0. It's just from your lower bound to your upper bound of x tilde dA. So x tilde, remember, is the centroid of your differential element. And then that's divided by the definite integral from the lower bound to the upper bound of dA. And this one is actually just the area of under the curve. This is like the first integral you ever did in calculus, and that bottom one's pretty easy. So, and if you notice between the x bar and y bar, the bottom is the same integral. So you're going to get to use that. If you're doing x bar and y bar, you do that bottom integral, and you get to reuse it again. Up top, the only difference is you're putting in y tilde for your y bar, and then for x bar, you're using x tilde. Okay. So you just integrate these, and we'll do an example of this.